Today on The Future of Everything, the future of democratic AI. So the impact of artificial intelligence, or AI, on our world is everywhere, and we've actually discussed it on The Future of Everything at length. We see AI in our faces when we talk to our smartphone, or our home assistant, or even our robotic vacuum cleaner. We also know that it's in the background when we shop online, choose TV shows and movies to watch, and even serious things like applying for credit cards or a loan. We hear, and we're starting to see, that it's entering medical care. It's helping make diagnoses, allocating medical resources, and even helping to provide home care to the elderly and the infirm. But all of these applications, for the most part, are brought to us by big business. Companies have made huge investments in what are called server farms, which are these huge physical plants running computers 24/7 that are using data typically to create the algorithms, the machine learning that impacts our lives and that we're starting to see in all these applications. The companies with the biggest farms seem to be winning the race, and they provide currently probably the best or most lucrative services. But what about smaller operations? What about small businesses, non-governmental organizations, philanthropies, even academics and researchers at universities? Is there any way that they can compete in creating useful, high-impact AI applications? Professor Kunle Olukotun is professor of electrical engineering and computer science at Stanford and an expert on the hardware and software that powers AI systems. In the past, he helped design generations of computer chips that brought massive computational power to things like personal computers and smartphones. And now he's thinking about the full set of problems facing AI development: hardware, software, and even some of the human elements like bias and fairness. Kunle, why have you decided to focus on democratic AI, and what's at stake here?
Well, I mean, everything's at stake, right?
Okay.
I mean, you laid it out, right? I mean, the future of the way that we interact with the world, the future of computing is going to be dominated by AI and machine learning. It's what's completely captivated, the whole of the computer science arena, from sort of what people are doing in machine learning algorithms all the way to what people are doing in hardware. And, so you talked about that this big trend of sort of machine learning being used everywhere. But I think the thing that people, of course, understand in the background, but maybe don't fully appreciate, is the fact that machine learning has been enabled by advances in processing and silicon technology, right? So the whole idea of neural networks and has been around for 50 years. And the way of actually training these networks using an algorithm called backpropagation has been around since the 80s, right?
I remember as a student dismissing them as interesting but irrelevant to my life.
Yeah, exactly. And so when Jeff Hinton got the Turing Award a few years ago, he stood up and said, well, you guys all thought, I was smoking something for the longest time. And now, look, it looks like I was right and you were wrong. But the only reason that he was right is because computation enabled these neural networks to be built with enough complexity, trained with huge amounts of data, such that they could actually beat conventional algorithms, right? And so it really was a triumph of not just the approach, but the amount of computation that you could apply to actually making these very complex models.
So as I described in my intro comments, there are these large companies that have unbelievable resources. Is that just going to be the way it is, or are you and others thinking about ways to bring that kind of power, as has happened before? The Cray computers of the 1970s are much less powerful, and 80s are much less powerful than my iPhone. And so, and it's folks in your discipline who brought that. But is it asking too much to bring me a server farm to my living room or to my lab?
Absolutely not. And that's exactly what we want to achieve, right? So this whole democratization is really about, what used to be supercomputer level power that you now have in your back pocket can be, or you can transform whole server farms amount of compute to something that is in a much smaller footprint, and can kind of liberate AI technology from the hands of the high priests in the large companies that want to sell you something into, the developer or researcher in the lab, or the domain specific sociologist who wants to train models that are much more specific to.
So let's dive a little bit, and I know this is complex stuff, but for people who are wondering, okay, that sounds like magic. Tell me the kinds of technical things that are beginning to happen that give you the confidence that we're going to be able to miniaturize and distribute this in a much more kind of global way. What's happening? What's happening technically?
So I think the key thing that's happening technically is this whole shift from what people have called traditional computing, software 1.0, to software 2.0, which is...
Okay, so that sounds good. So tell me about what's 1.0 and then what's 2.0 going to be?
You're right. So 1.0 is traditional, high-level language coding in C++, Java, and traditional Python, where you as the programmer are faced with a problem, you decompose it into components, you come up with specific algorithms for those components, and then you put them together, right? So that's software 1.0. Right?
That describes all the programmers currently working at the big tech companies. They sit down and they write code in a very structured way to solve a specific problem.
Right.
And if you have enough of them, you've solved a lot of problems.
Exactly. But there are some problems that are very hard to specify, right? Such as, how do I know that I'm looking at Rust, right?
Scary,
that would be a hard algorithm to describe, right?
Okay.
So what we want then, so the approach, of course, that a lot of machine learning has taken is let's build a neural network that actually learns what Rust looks like, right? Okay. And if we show this neural network enough pictures of Rust, and we say, this is Rust, from all different angles, then all of a sudden we have a Rust recognizer, right?
Okay.
And of course we can generalize it so we can recognize it.
Yes, and so is that an example of software 2.0?
That's an example of software 2.0.
Right. So just to highlight the differences, there wasn't just right. Go ahead.
The programming is essentially the weights that get set by this optimization process called training.
Right.
Okay.
Right. So there's never anybody sitting there writing a piece of code.
There's a general structure that gets defined by the machine learning expert, but the actual weights, that structure, to make it a very good analogy, that structure you might think of as a newborn baby, right? The newborn baby needs to experience the world. They've got the brain, they've got the capability, but they don't have the experience to actually, define the connections with the neurons in their brain such that they can actually do interesting things.
It's actually how I sometimes describe graduate students, as they have great hardware, but they're empty, and we need to fill them up with useful capabilities.
Exactly, right. So this software 2.0 then is all about these networks that you define, and then training those networks with huge amounts of data so they can do interesting things.
Gotcha. Okay, so this is a new way of getting capabilities, very different from somebody sitting and writing a linear sequence of instructions. It's instead, here's a million examples of what I want. Please learn what I want. So but now I'm very interested that your first answer was software 2.0, because in your heritage, you are a hardware guy. So I presume that vision for software 2.0 has very fundamental implications for the kinds of hardware we need. Is that true?
Yes, exactly. I mean, that's exactly where we're going. But of course, one has to enable the other, right? Just as kind of, advances in GPUs enabled us to build these new ML and AI capabilities. So now that we're at the point where that's the dominant way of, or becoming the dominant way of developing software. So what kinds of software do we get? We get this connection of components in a graph that we call a data flow graph, right?
Okay.
And so what we have is a data flow graph of components where the kernels of compute could be matrix multiply, it could be convolution, it could be some other machine learning operations. But the key idea is that the whole application is composed of multiple kernels that communicate in very specific ways.
Yeah, so you've written about this data flow, and I want to make sure we flesh it out a little because it might not be immediate, intuitive to people. So I take it that previous computational approaches have not been particularly data flow oriented.
Well,
how new is this, I guess, is my question.
Data flow is actually an old idea.
Oh, okay.
It's an old idea, but it really is, you know, to dive into it really is a question of sort of at what level are you looking at data flow? Okay. One can think about the communication between different instructions in a conventional CPU as data flow, and it has been called data flow. But that's not what we're talking about here. What we're talking about is a much more macroscopic view of data flow between these computational kernels in the machine learning computation graph, right?
And is this literally the flow from one computation to another? To another. Electrons going through wires from
data,
one unit.
Yeah, electrons, wire, you actually have data, they're usually called matrices and tensors and so on. That is the data flow, right?
Okay. And
so back to your question of sort of what implications does that have with hardware?
Yes.
Well, the way to think about what is being designed so far is that conventional computers are very good at software 1.0, right? They're optimized for control flow, right? Following branches and deciding
if this, then do that.
If this, do that. And then this idea called caching, right? And caching is this automatic way of bringing data close to the processor so that you can effectively process on it and spend a little time accessing data.
Right. I think about caching as I'm going to need this in a minute, so I'm not putting it away in the closet. I'm keeping it on the kitchen counter so I can grab it when I need it.
Exactly. Because you accessed it something recently, there's a high chance that you're going to access it again. So keep it close, right? That's caching for you. So that works very well for traditional 1.0, right? So 1.0 has these processors in them, right? These general purpose processors. So we've made tremendous strides over the last, 30 years at improving the performance of these processors using the bounty that Moore's law has given us. And this, of course, has driven the huge amount of computing capability that, of course, has driven the whole economy, right? It's driven the whole world, right?
Yes.
But these things are fundamentally inefficient. If you look at how much energy goes into actually doing the computation that moves the program forward, you roughly spend 10% of your energy doing compute you really care about.
And you're talking about electrical energy. Electrical energy. This is
electrical energy, right?
It's not some fluffy idea.
Yeah, yeah. Okay. The watts that come into the computer hardware. There's some, by some measure, 90% of what power you use, you kind of waste in that you don't actually use it to move the computation forward.
Okay.
Right? So then conventional processors put multiple of these inefficient computational devices together to get more power.
Yes.
And they even get more inefficiency. They spend 99% of their time moving data around.
Yes, and just to be clear, you say more computational power, but it's at the expense of even more electrical power.
More electrical power. Yes, yes, exactly. Thank you for clarifying that, right? And so, okay, so what's the alternative? The alternative is, why don't I build a specialized piece of hardware for the algorithm that I need, right? And if I did that, I would get 1,000 times more efficient execution, right? So one example of this would be you know, how is it possible that I can, on my iPhone or on my iPad, watch a movie, you know, for a long flight across the country, right? When we used to fly,
Yeah.
right? Well, the reason is there's specialized hardware in your mobile device or in your iPad for doing video decode, for taking the compressed version of video that sits in your storage and converting it into something that is a high definition movie that you want to watch, right?
Right.
That is a very specialized algorithm.
Gotcha.
And the way that, and so if you were to try to do this on a general purpose processor, you know, maybe your battery would last you know, half an hour, and then
right, you could barely watch the
barely
trailers.
watch the trailer, right, before you.
Okay, so what I'm hearing you say is that the thing about software 1.0 was that these very general purpose computers, which
Yeah.
are great because they're general purpose, and so everybody can do whatever they want with them, but
Yeah.
that comes at a huge inefficiency. And if
Yeah.
we're going to want to get the next step, we're going to have to perhaps, and this is what I want to ask you, are we looking, perhaps we're moving away from everybody has a general purpose computer, and in fact, many of our computational devices become purpose built.
Yes, but purpose built for this very general paradigm, right? So, and not, you know, and I talk about these specialized hardware to show you two ends of the spectrum, right?
Yep.
One very general that can do anything but is pretty inefficient. One highly specialized and fixed, but that's the problem. It can't change. And so if your algorithm changes, if you want to do something slightly different, that fixed piece of hardware won't do the job, right?
Right.
And
Gotcha.
so what you need is, you know, you'd like the best of both worlds. And how do you do that is this new idea of what we're calling reconfigurable data flow.
Right. Right. Okay, we got to get to that. So, but just to summarize, because I think I do understand, we're not going to have hardware that recognizes Russ's face. We're going to have hardware that recognizes faces or images, and then we will specialize it to be for Russ when we need it, but it'll be for Kunle or for cats or puppies in other examples.
Even more general than that. What we want is something that can be used to make face recognizers or be used to make natural language processing.
Okay, so the generality is pretty broad.
You want the whole set of algorithms that machine learning is interested in to be able to run on this piece of highly optimized hardware very efficiently. All right, and that's the key. The key is that if you want something just to do face recognition or just to do visual recognition, that's a more specialized piece of hardware than something that's more general for all of machine learning.
This is the future of everything. I'm Russ Altman. More with Professor Kunle Olukotun from Stanford University about software 2.0, hardware 2.0, data flow, and applications of these incredible technologies next on SiriusXM. Welcome back to the future of everything. I'm Russ Altman. I'm speaking with Professor Kunle Olukotun from Stanford University, and we're talking about the future of AI and the software, hardware, and applications that it will drive. So at the end of the last segment, we were just beginning to get into this, which sounded to me like a little bit of a complicated idea, which is data flow computing. And it's a key part of what you're calling software 2.0. So take us through how we should think about data flow computing.
So the way to think about data flow computing is really, it comes down to sort of how you get performance from hardware, right? And there are two pieces of the puzzle, right? One is what you do in the compute, right? How you do the adds, the subtracts.
So the nuts and bolts of
nuts and bolts of actually
moving bits around.
Moving bits around. And the other part is how exactly you move the bits around, the communication, right?
Right.
And you need to balance these two, right? To get high performance. If you had very efficient compute and very inefficient data movement, you wouldn't get good performance.
Right, because you had just done this great computation, but now it takes forever to pass it on to the next unit that needs it.
Exactly, right? And so the great thing about this machine learning software 2.0 approach is at the very high level, the way that the machine learning application developers develop their application, they tell you, they give you a map of how one piece of the computation communicates with another piece of the computation, right? And this is this big graph. It might have hundreds of nodes in it, right?
Okay. Okay.
Now, if you take a software 1.0 approach to executing this big graph, you execute things one kernel at a time. And then you...
When you say kernel, you mean that whatever that computation is.
That's a computational component, which is kind of a key component of all machine learning algorithms, right? It's composed of multiple different types of kernels. But just think of these kernels as these highly intensive computational elements that can be reused, right? So for those of you who know anything about, you remember your introductory linear algebra course, matrix multiplication would be an example of a kernel, right?
Well, even regular multiplication, take two numbers, subtract them, and give me the answer. That's a very small, trivial
There's a very small kernel, exactly, yes. But typically what the nature of computation for these machine learning algorithms is that you have what are called vectors of data, right? So you might, each vector might have, 1,000 or 10,000 elements in it. And so you need to do this multiplication 1,000 or 10,000 times, and then that's your kernel.
Right. Got it.
Right. Got it. All right. Now, so you've generated the result, and in the software 1.0 approach, you dump that result in some random memory location, right? And that random memory location is off chip. It's off. You've got your computational component, and you've got your memory component.
Right.
And you put the result of the computation off chip on the memory, right?
Yep.
So now that when the next kernel comes along, it's got to go and fetch that data from off chip and bring it on chip.
That really does make sense. Yes.
That takes a long time. It takes a lot of coordination, and it burns a lot of power.
Okay, so there's the key. That's where we were wasting the power.
We're wasting a lot of power because you are not, the direction said go from, point A to point B. And what you did was you went from point A to point C, D, and E, and then you finally came back to point B, right?
And all of that cost energy and time.
And time, right? So what we do with data flow computing is we take our cue from the way that the machine learning application was defined, and we lay out the computation in space instead of time, right? So instead of doing one kernel at a time, one after the other, we're going to do all the kernels in space, right? And then to add another wrinkle, we get what's called pipeline or assembly line the computation.
And when you say space, you mean that there will be chips literally where the kernels are sitting on the chip.
In particular, there'll be parts of the chip devoted to each of the kernels.
Right.
And and we could go into details to why we can do that, but let's just assume that we can do that. Now, the communication between one kernel and the next happens very, very efficiently on chip. Right, the data just moves over.
I could imagine that if there's a fast wire and if they're physically close as well, then not only will it get from A to B quickly, but there'll be the minimal number of electrons and power required to do that.
And you bring up a good point. So one of the things that the software that does what's called mapping to this architecture has to do is it wants to put things that communicate a lot close together on the chip so that they have this very efficient pathway.
Okay, so that actually really does paint the picture. I can really see now that the software 2.0, we're talking about chips now that have a very different look. Even when you look at them with a microscope, they're going to have like these little areas of the chip that are kernel 1, and then the other kernels or the other computational elements that care about the output of kernel 1 will be closer to it, so that they can get the data and do the next step. And then you'll actually watch it go, let's say, from left to right. And when you get to the far right, you're done with your computation. And so that kind of makes sense. So let me ask you, how far away are we from this reality?
One more point before we get to that is that the key to this, right, is you can reconfigure things, right? So it's like an assembly line that you can reconfigure it. So today you're making a truck, and tomorrow you're making a four-door sedan. So you set up, it's roughly the same assembly line, but you set it up a little differently, and now all of a sudden you get programmability and flexibility.
And I could also imagine that if you had it laid out, and then when you ran it, it was disappointing, you might actually realize that you did the layout wrong, and you fixed the layout.
Exactly.
So how far is this? Is this a fairy tale, or are we going to be seeing this anytime soon?
No, we actually have, so about 3 years ago. So the interesting thing about this is we came up with these ideas at Stanford maybe 4 or 5 years ago. But 3 years ago, we started a company called Samba Nova Systems, Chris Ray and Rodrigo Liang and I, to actually commercialize these ideas. And the company is called Samba Nova Systems, and we have a 40 billion transistor chip called the Cardinal SN10 that's available today.
So we in the remaining 1 minute and 1.5 minutes, who are going to be the early adopters of this technology? I'm sure, especially if there's a company, you have to think about who your customers are. So who are we going to see uptaking this kind of new paradigm?
Currently it's being deployed at the national labs, and so these are the first customers of.
What kind of computations are there? Paint for me a little picture of
the
kinds of applications.
They're doing all sorts of things. They are doing high resolution astronomy models. They're doing it to do molecular analysis for COVID-19. They are using it for doing some graph neural networks. They're using it for doing materials.
So this is quite broad. So it's delivering on the promise that you made earlier. That these
and one of the issues is, of course, one of the examples is that a lot of the AI for science, there's this whole idea of surrogate models, which you're probably well aware of, where people are trying to replace some of the traditional simulation and with machine learning and AI models, and so it's being used for that.
Super exciting. Well, thank you for listening to The Future of Everything. I'm Russ Altman. If you missed any of this episode, listen anytime on demand with the SiriusXM app.